All right, so we are back in our FBI suits to re-question another victim in the police files that encountered the change in entropy during equilibrium. Now, knowing the importance of delta S in the universe to predict spontaneous change, we definitely want to get more details of what happens at equilibrium. So for any process that's going to be approaching equilibrium, we know that delta S naught of the universe is going to be greater than 0. But once we get to equilibrium, there is no further net change. So delta S of the system and delta S of the surroundings are going to be balanced. This means that it doesn't matter what delta S of the system's value is. Delta S of the surrounding will have an equal value of an opposite sign. So if delta S of the system is negative 10, then delta S of the surroundings will be positive 10. All so that both of them can equal to 0, and therefore delta S of the universe will also be equal to 0. We can also rewrite this and say delta S of the system is equal to negative delta S of the surroundings, or vice versa. If the system is negative, the surroundings will be positive. Again, it's all about equaling 0. So when a system reaches equilibrium, neither the forward nor the reverse reaction is spontaneous. So there is no net reaction in either direction. And this delta S of the universe helps us verify that. So of course, we want to go further and look at an example. Let's calculate delta S of the universe for the vaporization of 1 mole of water at 100 degrees Celsius. Of course, 100 degrees Celsius is 373 Kelvin. Now, since we are talking about things at equilibrium, if the forward reaction is going from a liquid to a gas, or vaporization, then the reverse reaction is going from a gas to a liquid, or condensation. So for this example, we can also say that we're calculating the vaporization condensation of 1 mole of water at 100 degrees Celsius, or 373 Kelvin. So in order to do this, we have to make sure that we're going to be calculating delta S of the universe. That means we need to get a value for delta S of the system and a value for delta S of the surrounding. We're going to prove how they should be equal to one another and have opposite signs. So let's start out to solve for delta S of the system. To solve for delta S of the system at a standard state, we can take the sum of the standard state of the products minus the sum of the standard state of the reactants. Since we only have one reactant and one product, we can simply say that 195.9 joules per Kelvin is going to be subtracted by 86.8 joules per Kelvin. When we subtract these two numbers, we get 109.1 joules per Kelvin. And again, these S naught values are going to be given to you in any type of calculation you would have to complete. Now that we have the delta S naught value, we can go ahead and get the delta S of the surroundings value. Now, delta S of the surroundings is equal to negative delta H naught of the system divided by T. So what is our system? Since we're talking about the forward reaction, our system is going to be vaporization. So we can say delta S of the surroundings is equal to negative delta H of vaporization divided by T. And we can go ahead and get the vaporization value for water. Now, this will also be a given value for you. And this given value was automatically converted to joules. But if you're also seeing it given a table with delta H values, you might have kilojoules per mole. So you want to make sure that you're going to convert to joules per mole, for example. Now, we're going to divide our delta H of vaporization value by our temperature, which is 373 Kelvin. And guess what we get? Negative 109 joules per Kelvin. So our delta S naught of the system was 109. Our delta S of the surrounding was negative 109. When we add these together, our overall delta S of the universe for this overall equation in equilibrium is going to be 0. And all we're doing now is verifying what we already know, that delta S of the system and delta S of the surrounding must have an equal value and be opposite sign so that they can equal to 0 for delta S of the universe at equilibrium. Okay, folks? Now, for the reverse change, where we're going from a gas to a liquid or condensation, delta S of the universe is also equal to 0. So it's still going to be equal to 0. The only difference is the sign of delta S of the surroundings and delta S of the naught of the system has changed. So this time, when we're talking about condensation, our delta S of the system will be negative 109, and our delta S of the surroundings will be positive 109. So like previously stated, when a system reaches equilibrium, neither the forward nor the reverse reaction is spontaneous. So there is no net reaction in either direction. Let's continue on and talk to our final victim of this lecture. All right, folks, we're on to re-question our final victim of this part of the lecture, who was focused more on enthalpy of the reaction instead of entropy. So to clear confusion, we let them know that a reaction occurs because of the delta S of the universe, which is going to be combining the delta S of the system and the delta S of the surroundings, so that it's all greater than 0 and ensures spontaneity. And this all happens regardless of any enthalpy change of the overall system. That means we do not care about the delta H value. We only care about delta S of the universe, which is going to be combining delta S of the system and its surroundings. And we focus on two ways this can happen: in an exothermic reaction or an endothermic reaction. So let's focus on exothermic reactions first. Now, again, we still are using this graph where we have our entropy going to be on the y-axis and the change in entropy for the system, surroundings, and universe on the y-axis. Now, we still understand if we wanted to figure out the amount of heat absorbed or released from a system, we can look at the delta H value. The delta H value is going to be less than 0 when we're dealing with exothermic reactions, versus the delta H value being greater than 0 when we have endothermic reactions. But delta H value does not tell us anything about the spontaneity changes of a system. In order to do that, we have to focus on delta S of the universe, which again is delta S of the system and its surrounding. For all exothermic reactions, the reactions will always be spontaneous, and delta S of the surroundings will always be positive. And this is going to be, again, for exothermic reactions. For endothermic reactions, the systems do not always have to be spontaneous. But if they are spontaneous, then the delta S of the surroundings will always be negative. Let's go ahead and take a look at our examples a little bit deeper. So for this exothermic reaction here, we have our solid and a gas mixing together in reactants to form all gaseous molecules that's going to release heat, okay? As you can see, our delta S of the system is going to be positive, and our delta S of the surroundings is also going to be positive. Since both of these values are positive, that means our delta S of the universe will also be positive. And if it's going to be positive, that means this is a spontaneous process. We can also have exothermic reactions where delta S of the system is actually negative. So if delta S of the system is negative, that means delta S of the surroundings has to compensate. Now, we already said that with exothermic reactions, delta S of the overall surroundings will always be positive. So as you can see, delta S of the surroundings is positive here. It's positive enough to compensate for the fact that delta S of the system is negative. And therefore, delta S of the universe will also be positive, and this overall system is spontaneous. For endothermic reactions, we said that delta S of the surroundings will always be negative. Therefore, that means that delta S of the system has to be positive, and it has to be positive enough to compensate for the negative parts of the delta S of the surrounding. It does that in order to have a positive value for delta S of the universe if this entire system is said to be spontaneous and endothermic. Okay, folks, so make sure that you go ahead and review your notes and your flashcards so that we can layer this information into the next part of the hunt. We can now use our new weapons to dig deeper into Mystic Falls and find a faster way to understand spontaneous changes to fight even bigger battles ahead. See you there.